How many postulates are there? There are 4 postulates or 5, depending on which book you read. But you will eventually see that what is 4 in some book is actually 5 in some other book. So this number is not very important. What is important that you understand what is meant in these postulates and why these are called postulates. Any idea why they are called postulates?
They are not derived from any more fundamental principles. They are just assumed before.
Yeah, who is okay, Charan? Yeah, yeah. So basically, it is these are something which you cannot derive or you cannot actually derive from any first principle. So these are like these are something which are given and you have to take it for granted. Okay, so you have to believe in these postulates. You don't question these postulates. You take these postulates and based on these postulates you build the subject, and end of the day you get this beautiful subject of quantum mechanics, and you can apply this formalism, this framework of quantum mechanics and explain things, explain how the subatomic world behaves. Okay, so in the last class we talked about de Broglie's hypothesis, also Heisenberg's uncertainty principle, qualitatively. We'll come back to that later, Heisenberg uncertainty principle. But today, as I mentioned in the beginning, we'll build the subject based on this postulate. So, what is the first postulate? So let me write it down first, and then I'll explain. Okay, the first postulate says that, maybe I use some other color. So I'm talking about postulate 1. Okay, postulate 1. Yeah. So the postulate 1 tells you, okay, it tells you that the state of a system is specified as fully as possible by the state function. And also this is known as wave function. And this function is usually written as capital psi, which is a function of space and time. So by space we mean x, y, like this, and time. So any question on this statement? This is just a statement of postulate 1. I hope everybody can see. If somebody cannot see, if somebody cannot see, please let me know. Everybody can see? Can you see the presentation? Okay, very good.
Yes, sir.
Okay, so let me state it again. The state of a system is specified as fully as possible by the state function or wave function. This is also known as wave function, and usually it is denoted by this, the one I showed here, a capital psi, which is a function of space coordinates like x, y, z, and okay, and time t. So basically, this is a function of space and time. Now, this function, which I'm going to call it wave function or state function, just this function does not really have a direct physical significance, but it has, it plays the central role in the framework of quantum mechanics. We'll see how. Now, what do I mean by the system, and what do I mean by state of a system? So let me think of a system like this. For example, let me write down. You can think about it. So, for example, I am in this room, and you assume that in this room, but you can assume you have a box. Rather, you have a box, and inside that box you have one, say, helium atom. Okay, so you have one helium atom inside the box, and you have one helium atom inside the box, and then what is your system? Your system is helium atom, and the available space is only the box, okay, within the box. So how do I describe that helium atom in the box? So you know that I describe that helium atom. For example, maybe this is your helium atom, which is inside the box. This is schematic only. And how do you describe this helium atom? It has some position x, some position y, some position z. So it has a position coordinates, which is given by set of x, y, and z, and also it is at some instant of time, and the particle, the helium atom, could be anywhere inside the box. So with time, if it's moving, then its position will change as a function of time. So in general, so if I want to describe this, say I associate a function with this helium atom, and I'm calling that as the wave function, which is a function of its position, which is x, y, z, and also the a function of time. And this is the wave function or the state function that describes that helium atom inside a box. So people are asking something like thermodynamics, temperature. So let me write down here, no temperature in quantum mechanics. So we will not talk about temperature. Okay, so no question of asking anything like thermodynamics or anything which has something to do with temperature. So there is no notion of temperature in quantum mechanics. Is this clear? So there is no notion of temperature in quantum mechanics. Quantum mechanics is there only in thermodynamics, and there is a subject called statistical thermodynamics or statistical mechanics that gives you a prescription to start from a microscopic description, either classical mechanical or quantum mechanical, and that subject also has set of postulates. Using those postulates, you can actually calculate some average quantities in that subject, which will relate to the thermodynamic quantity, and you have temperature in that case. But in quantum mechanics, there is no temperature, no notion of temperature. You will see throughout this course, we rarely mention temperature. Is this clear? Like a person who is doing quantum mechanics, uh, usually say, okay, I am doing theory which is zero temperature, which basically means there is no temperature. Okay. Yeah. Yeah. Somebody has a question. Who has?
Yes, sir.
No constant. No, does not mean there is no notion of temperature. In quantum mechanics, in the there is a subject called quantum statistical mechanics. There you have temperature. But the course is on quantum mechanics. In quantum mechanics, there is no notion of temperature. We don't know what is temperature. Don't talk about temperature. It is like that. Okay. So don't ask this question. We cannot ask a question which involves the word temperature. We don't know what is temperature. There is no concept of temperature in quantum mechanics. Yeah, someone was asking a question, I think, on the chat box. Okay. Someone has a question other than Gautam, maybe someone else. Who had it? Let me check. Devojit. Hey, ask me. Devojit?
Yes, yes, sir. I was
Yeah,
asking
tell
that
me.
temperature thing is generally defined for bulk body, macroscopic bodies. So the notion of
Hmm.
temperature is not defined for microscopic bodies. That's why
No,
is
no, 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 not really. No. Let me tell you, not really. You're right. But for example, I can have a box where I have not a single helium atom. I have, say, 1 mole of helium atom. So then you have a bulk in a sense. You have a big number of particles. But if you're doing quantum mechanics, we will not talk about temperature. We'll talk about these helium atoms who are, these atoms are maybe interacting with each other. Essentially, it will be a quantum many body system, but without temperature. Still, we are not having temperature. You have to bring temperature from outside in quantum mechanics using the framework of statistical mechanics. And when you actually join this, when you actually bring these two together, quantum mechanics and statistical mechanics, what you have is quantum statistical mechanics. And there you have temperature. And the example of quantum statistical mechanics is best examples are like Fermi-Dirac distribution of electrons at temperature T, or Bose-Einstein distribution for photons or phonons at temperature T. These are examples of manifestation of what is known as quantum statistical mechanics of subatomic particles. Where you have quantum mechanics because these particles are quantum mechanical, but at the same time you have now n number of particles, and also you have this what is known as temperature. Okay, but in the subject of quantum mechanics, it is very important that the subject of quantum mechanics does not have what is known as temperature. There is no temperature. Okay. And someone is asking me, what do you mean by state? The state of the system means, for example, in classical mechanics, if I know the particle is here, it is the state of the particle is completely defined by its position and velocity or momentum. In the quantum mechanics, similarly, the state of the, or essentially the state of the system is completely or fully specified by this wave function. If I know the wave function, I know the state, because we will see eventually that when you build this object just by introducing postulates, you will see that when you know the wave function, and there is an equation called Schrodinger equation, the wave function follows that equation, which will come later. Then you know how to calculate quantities which are observables, and then how to connect this with experiments. So very useful. If I know the wave function, then I can use this prescription to calculate observables and then connect this to experiments. So that's why, that is what is meant by the state. Okay. So, but is this clear that the state function or wave function is a function of space as well as time? That is important. It is not a function of space only. In general, it is a function of space as well as time. Is
Sir,
this clear? Yes.
Sir, suppose we consider some model system, suppose particle in a box. So what if we specify two temperatures, two different temperature for the same system? So will the wave function would be same? Every
So I
parameter
told
would
you
be
that
same or what?
no. Don't bring temperature in this course. There is no notion of temperature in quantum mechanics. That you have to understand. There is no concept of temperature. So when you have the subject, you don't know what is temperature. So you cannot bring something which you don't know, which does not exist in the framework of the subject. You understand?
Yes, sir.
So you cannot ask this question even. If you have two temperatures, then you are actually doing statistical mechanics. You're not doing quantum mechanics anywhere. Maybe your system is quantum mechanical, then you are doing quantum statistical mechanics, which is a completely different subject, not quantum mechanics. Yeah, it is
Okay, sir. Fine.
built on
Thank
quantum
you.
mechanics, but then it's a marriage between quantum mechanics and statistical mechanics. So please keep it in mind that there is no notion of temperature in quantum mechanics. Some of you are going to work in computational lab, and eventually you will do some quantum mechanical calculation, and then you will calculate some thermodynamic properties. But when you make that jump from quantum to thermodynamical properties, either knowingly or unknowingly, you are entering to statistical mechanics. So you are bringing some distribution, which is a temperature, like Fermi-Dirac, Bose-Einstein, or Boltzmann, whatever. Okay, and then from there you can calculate thermodynamic quantities such as entropy, free energy, etc. But quantum mechanics, by definition, there is no notion of temperature. Hey, Rahul, you want to add something? Rahul, are you there?
No. It's perfectly fine. That I mean, usually the quantum mechanics that you do is zero temperature. By zero temperature, I mean zero Kelvin. So as long as you
Yeah,
have
you
the
can
zero,
think it is a 0 Kelvin, but or you can think there is no notion of temperature here.
yes.
So don't
So
talk about temperature.
basically, it's absolute. I mean, zero temperature. So there is no thermal fluctuation as in inside built-in quantum
Yeah.
mechanics.
I did not want to say that because they would not know it.
So if you
what
add
he's
on
saying
the
that
if you bring
if you
in
take
temperature, if you bring in temperature, you are actually adding some additional degrees of freedom due to your thermal fluctuations, which usually in the framework of the quantum mechanics you don't do.
Yeah.
So
when you
if
do, actually you go to quantum statistical mechanics.
Yeah.
Because temperature is comes from there. So there is no temperature in quantum mechanics. The subject I want to deal with today. Okay. So now you know what is wave function. At least you know the statement, what we mean by wave function. Now why it is so useful, this wave function? Now wave function is very useful because it tells you that, so for example, in this case, here is your helium atom. I know the position and I know the wave function. Then at this position, what is the probability of finding that particle? In this case, helium atom. So what I do, I don't have one point, but I consider a small volume element around that point. Of finding the helium atom or that particle or that system. In a small volume. Sorry, I am not writing it very smoothly because I am not very comfortable. Volume. Now, what is a small volume? Can anyone tell me? Can anyone tell me what is that small volume in that picture? So, for example, if this is your x direction, this is your y direction, this is your z direction, then this small volume could be something like dx. This is dx, this is dy, this is dz. So it's a multiplication of these three tiny lengths. These are tiny lengths: dx, dy, dz. Okay, I'm calling the whole thing as d tau. This is the notation I'm going to use. Huh? So I have a very small volume. It's a parallelepiped, which is a volume d tau. Then what is the probability of finding this particle, helium atom or anything in your system, within that small volume element? Is actually, it is obvious that it should be proportional to that volume element, isn't it? As I make this volume element smaller and smaller, smaller and smaller, or bigger, what will happen? If I make it slightly bigger, then it is more likely that the particle will be found there, isn't it? So it should be proportional to that volume element d tau, which is dx times dy times dz. Dx into dy into dz. Is this clear? And not only that, actually, then what you need to do, you need to know this wave function. And this wave function, which is a function of x, y, z, and time, you need to know the wave function. And not only the wave function, you have to, in general, this wave function is a complex number, could be a complex number, could be real or could be complex, okay, in quantum mechanics. So if it is complex, the probability has to be real. No, probability is something which is real. How you make something real? If you have to express that in terms of some complex function. So that was given by Max Born, and he says, okay, the probability of finding that particle within that volume element d tau is proportional to that volume element d tau, and also, more importantly, it is proportional to the square of the wave function. Okay. But this wave function could be complex, so you have to take the what is known as
complex conjugate.
What is known as the complex conjugate of the wave function multiplied with itself, and then multiplied with the volume element. So this psi mod square, which essentially means you are doing psi star psi. Basically, what I have here is psi star psi times d tau. Is this clear? So this is the probability of finding that particle within that volume element d tau, provided I know the wave function, which is psi. But psi could be complex number, so I should not take only psi square. I should take psi star and then multiply psi star with psi. Okay. So the psi star psi, this thing other than the volume element, this is called probability density. So this is called probability density. Okay, and you multiply that probability density with a small volume element, that gives you the probability of finding that system or that particle within that volume element d tau. Is this clear? If you have any question, please let me know. Okay, now you know the probability has to be real. It cannot be negative and it has to be real. So I told you what is the probability of finding the particle within that volume element d tau. Then what about the total probability? What is total probability? Now total probability means what? If I go back to that previous picture, in that previous picture, let me draw it again. So you have this particle, this helium atom, whatever you want to call it. It could be an electron as well. This is in the box. It's a very badly drawn box, but please bear with me. And I told you that this particle cannot go outside the box, so it has to be within that box. And if I don't have that box, I can have a situation like that. Okay, this helium atom is free in the universe. So it could be anywhere in the universe. Okay, this is another way of saying this. So it could be anywhere in the universe. It could be anywhere in the universe. And in that case, what I'm going to do, I'm going to say the total probability, whatever, if you try to find this particle in the universe, for any case, what is the value of total probability? Can anyone tell me? So if you try to find this in the universe, it has to be there. No, it cannot go outside the universe. Or if your universe is only the box, then it has to be within the box. It has to be one. It's very simple. So what I have here now, what I have here is as follows. I have this psi star, which is a function of x, y, z, t. Then I have another psi function of, sorry, this is capital psi, function of x, y, z, and I had the volume element d tau, and now I integrate this, the whole thing, from minus infinity to plus infinity. If I assume that everything is within the universe, these are the two possible limits. And if I do this, what is the answer? Tell me what is the answer. Can anyone tell me what is the answer? Yes.
1, sir.
Yeah. So this is 1. It has to be 1. So if I take psi star, multiply it with psi, then integrate over whole space, you get equal to 1. Okay, one thing I should say that I prefer, and which is technically correct, that you write psi star first, then psi. Rahul, you understand what I'm saying? This. Rahul, are you there?
Yeah.
So it is better to write psi star then psi, because if I go to Dirac notation,
Yes,
it will be quite
yes,
useful.
yes.
Like people casually write psi star, but actually, strictly speaking, you should write psi star psi. And the volume element you can write after that or before that, doesn't matter. We'll introduce what is known as Dirac notation later, but not now, and things will be easier, I hope. So this is what is known as the total probability is conserved equal to 1, and this is it should be there, it should be possible. For example, if I say, okay, say I have a case where I have a wave function where when I calculate this integral, well, let me write down that integral again. I'm not writing x, y again. This is not equal to 1, but if you see that this is equal to something like a constant a constant. Okay, so if it is a constant, then what is the solution? Can you do something? Any suggestion?
So then we have to normalize the wave function.
Because you guys know, yeah. So, but you know there's a condition on probability. The total probability has to be 1. But if you don't find it to be 1, the integral is something like a constant a. For example, a is 10. Say a is 10. Then what you should do? Actually, you should now go back and correct your wave function, which is called normalization, so that you fix your wave function in such a way that now if you take psi star psi and integrate over all space, you get 1. So essentially what you do, so basically, basically what you do is your, write it here, you take psi star and divided this by root over a, in this case 10. In general it is a, the constant. Okay, let me write down that 10. And then multiply with psi, which is also divided by root over 10. And now you do this. What are you going to get? And this will satisfy this condition, isn't it? So what you do, you actually normalize the wave function so that the wave function or the state function, so that your total probability is conserved and that is equal to 1. So actually, by saying that, what I am doing, I am telling you a condition. This is the condition. What is the condition?
Rashid, in the equation that will be 1, not 10.
Yeah, but what I'm saying, that is equal to 1 here.
In the equation, you don't know that psi star by 1 root 10. I mean, mistaken, you have written 10.
Yeah. Sorry. Here, no.
Yeah.
The typo.
Yeah.
This one, no? Yeah.
Yes.
Yeah. So as I was telling that, okay, you have to normalize the wave function. Okay. So now, so as a result, you see that you get a condition. What is the condition? Condition is shown here, and the condition is this. So your wave function has a condition. What is that condition? Which is psi star of psi d tau integrated over all space is equal to 1, or any finite number which can be normalizable, like here. So it essentially tells you that your wave function, there's a technical word to this, is or has to be square integrable. You understand the statement? You understand the statement? Any question on this? Now, it appears that okay, it is possible, but you'll see there are cases where it's not possible. But we'll talk about it later. Example I can give you. For example, think of that your wave function is given by exponential of x or x by 2, and try to do this. And your wave function is such, and your particle could be anywhere in the universe. Try to square this, because complex conjugate of that is the same. It is a real function. To square it, it will be exponential of x, isn't it? And then try to integrate it from minus infinity to plus infinity. You will see that it is not finite. It will blow up. The integral is infinity. Is this clear? Any question? So I multiplied its complex conjugate, which is also this, and try to integrate it. Say I am only in one dimension, and this is going to be okay.
Hello,
yes,
sir.
So in this case,
sir,
this function is not square integrable. So this kind of function is not accepted as a wave function. Yeah, tell me.
Yes, sir. I have a question, sir.
Yes.
Sir, why we are taking the psi star here?
So we are taking psi star because psi could be complex conjugate. So if I multiply psi with psi star, it ensures that the psi star psi is a real number.
Sir, only for making it the real number.
Yes, because you are associating this with probability. It has to be positive real number, isn't it? Probability cannot be negative, cannot be imaginary. So you have to do, so multiplying with itself, that makes you positive. But since it could be a complex number, you have to multiply not with itself but with its complex conjugate, so that psi star psi is a real positive number, because you associate this with probability. Is this clear?
Yes, sir.
Yeah. And for example, if I have a function like exponential of x, it is not acceptable because it is not square integrable. So your wave function has to be square integrable. This is one condition they already introduced. What is next? So now next
Hello,
is
sir.
yes. Tell me.
I have a question that you have written the function and it is dependent on time. Then why there is no dt when we are integrating it?
In general, it depends on time, but I'm talking about probability at that instant, at that time, that particular time. Okay, the time is fixed.
Okay, sir.
That's why I am not indicating what time. So in most of the chemistry, first part of chemistry, you'll see that you're dealing with stationary states where your probability density, psi star psi, is time independent. Okay, that is also the case in most of the time. Okay, so now next thing is, since this is a probability, you have to understand that if I have a wave function psi in such, psi is such that, okay, I take psi star psi and I calculate that value at each point, and I find that, okay, at a particular value of x, or say assume one dimension just for simplicity, in one dimensional system. So or you can have a in 3 dimension also. Let us assume one dimension for simplicity. At that value of x, your psi star psi has more than one value. What will happen? Can anyone tell me? You understand what I'm saying? Is it acceptable? Is it acceptable? Any answer?
No, it's not.
Yes, somebody says no. Yes, and it is also, you can understand why. For example, I say, okay, my wave function is such that at a particular value of x, it has two values. What does it mean? I calculate the probability at that particular value of x, and I get two values. I get two values. One is 0.1, one is 0.3. So then I am confused. I don't know which value to take. So the probability has to be real valued, positive, and also probability at particular value of x has to be unique. It cannot have more than one value at that particular value of x or any space coordinate. Is this clear? Which essentially tells you that the wave function psi has to be single valued. For example, if I take a wave function, say it is given by a function like sine inverse x. Okay, and you see that this function is, say, 0 at 0, isn't it? Pi, 2 pi, like this, isn't it? N pi, you know that. It is not a single valued function. Is this clear? It is not a single valued function, sine inverse x. So this function cannot be an acceptable wave function. So wave function has to be square integrable, which I have already told you, and it has to be single valued. Okay, is this clear? Any other condition on the wave function? Anything you can think of? Anything you can think of other than these two? Now I have this helium atom in that box, no? And I know the wave function. If I see the wave function is such that at some point there is a sudden change in the wave function value. Sudden change. What does it mean? It means that wave function is not continuous. It's not continuous. Then I have a problem, because if the wave function is not continuous, then I have a problem, isn't it? Okay. So the wave function has to be continuous also, because it is single valued as well as continuous. And one more thing. Let me give you an example. Okay. So the example is, okay, Harsha, we'll see all these things later, functional forms. So let me write down a wave function which is so I am taking only the position part. Okay, it is exponential of minus x square. Can anyone plot this?
Yes.
Yes, sir, it's a Gaussian.
Yes, it's a Gaussian. Okay. Okay. So let me draw this function. Sorry, very bad drawing. It is x, and if I plot the psi wave function here, at 0, exponential of 0 is 1, so it will be something like here, this is value 1, and it is, if I change x to minus x, this does not change, it's a symmetric function, and it is actually behave like this, and in the, when x is plus infinity or minus infinity, it will go to 0. This is called a Gaussian function. What do you think, this wave function is acceptable? Is it acceptable? Any idea? Somebody says no. Why no? It is very much acceptable actually. You'll see and you will encounter this wave function later. This is the ground state of your harmonic oscillator. You'll see later. Okay, this is acceptable. But maybe I can give you some another example. So, what if, so let me give an example. Sorry. Now, if I have a wave function like, if I have a wave function like this, psi is given by exponential of minus x square, this is phi, by 1 plus exponential of 1 over x. Okay, I think that's the equation. Yes. Sorry. Minus. Now tell me whether this wave function is acceptable or not. Can you plot this wave function? Maybe you have to plot it first. So let me draw the axis. X. So what happens when x is very large? Can anyone tell me? When x is very large, what happens? X is very large, it is 0. Okay.
So then e raised to the power minus 1 by x is equals to 1.
Okay. So let me draw this half. Actually, this half is almost like a Gaussian, isn't it? This half. What is the value at x? Say, now I have to calculate the value. So if I approach from right hand side, approaching from right. If I approach from right, I am approaching x 0, but from right, huh? So basically, x is slightly above 0, so 0.00001. What will be the value of this wave function? Can anyone tell me? Devojit says 1. So just check this, because if x is, for example, x is very small, say x is, I don't know, x is 0.001. What will happen? So if I plot x 0.001 here, square of that will be even tinier, and you're taking exponential of minus of that. Okay. essentially you're taking exponential of minus of that, and so this will give you what? It is something like 1 over exponential of a very small number. So essentially it is 1. This part is 1. Is this clear? Is this clear? What about this part? This part, exponential minus 1 over x. What will happen to that part? Can anyone tell me when you approach from the right? Can anyone tell me? See, if you approach from the right, again, exponential of minus 1 by x. X is very, very small, very, very small. You're divided 1 by very, 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 very small. So your 1 by this is what? It's very, very small, isn't it? No, it is very, very large actually. 1 by very small number. It is actually very large. It is approaching very large value. And you're taking e to the power of minus of that. Here you're taking this. And that will give you what? 0. So when you approach this function from right, what you're going to get? You're going to get something like this is like 1 because it is e to the power of 0, and this is something like 1 plus something like e to the power of minus very large number minus infinity. So this will give you what? 1 plus 1 divided by 1 plus 0, and that is equal to 1. So if I approach this function from right, so the value of this function at x is equal to 0, which is here, x equal to 0, which is here, the value is 1. Are you convinced? It is very important that you get convinced. Okay, now do the same thing from left. I just approach 0 from left with the negative value of x. The good thing about this guy is it is symmetric. This part is symmetric. So if I approach from left or right, does not really matter. But this part, the denominator is important. What will happen to the denominator? What will happen? Now think again. Your x is small, but very small negative. Is this clear? So now what I am doing, I am saying, okay, x is small, but very small negative. So x is say minus 0.001 or even smaller. So what will happen to this function exponential of minus 1 over x? This is going to be exponential of minus 1 over, and this minus will combine to give plus 0.001, which essentially tells you it is e to the power of a very large number, like almost like e to the infinity, isn't it? But in the function, it is appearing in the denominator. So essentially, what you have in the denominator is 1 plus e to the power of infinity, which is also very close to the power of infinity because you can neglect 1. And since it is in the denominator, you have something divided by the power of infinity, isn't it? Something divided. And this is equal to what? 0. This is approaching 0. So if I approach the same function from left, what is the value I get? What is the value I get? Can anyone tell me? Write it down there. I think people have already written down. So the value you are getting is 0. So if I now plot this function, what is going to happen? So at this point, the function has two possible values. So approach from right and approach from left. So what is happening that again it is not a single value function at that point. You have two values, and then this function it is not acceptable. Is this clear? Is this clear? And actually, if you plot this function, you'll see that the function will look something like this. It is 0 here, and then it will go like this. Sorry, it will never become negative, but yeah, it will be something like this. Very bad drawing, but I'll now show you what this on something called Mathematica. So these are a function. Okay, and if I plot this function, let us see what happens. It's already shown there, and this is exactly the function. Can you see, all of you? So at this value x equal to 0, you have two possible values, 1 and 0. So there is sudden drop, isn't it? So these kind of functions are also not acceptable. Is this clear? Is this clear? Okay. So this is another condition, so which should be satisfied in quantum mechanics. So this is mostly all about postulate 1, and we're moving to postulate 2. Let me finish postulate 2 and then we come to discussion. We cannot finish postulate 2, but we'll do roughly. At least we'll introduce postulate 2 today. So what I'm going to do, I'm going to write postulate 2 here. Sorry for this. And the postulate 2 is as follows. It tells you that corresponding to every observable there is one linear Hermitian operator. This is a statement of postulate 2. How many of you know about it? How many of you? Just write it down on the chat box. Very good, I got 1 or 2 replies. Akash, yes. So corresponding to every observable, there is one linear Hermitian operator. Okay. So now I have to stress on 2. There are 3 things which I have to stress. What are this? The first one is this. So let me take this color. So I have to define what do I mean by observable. What do you mean by operator? There are 4 things actually. And if it is an operator, what is a linear operator? And what do you mean by the word Hermitian? All these 4 words are very important in quantum mechanics. Do you agree that these 4 words are very important in quantum mechanics when you build a subject? How many of you agree? Devojit, do you agree that these 4 words are very important?
Yes, sir. But I am not sure about this. Why linear?
It has to be linear. The quantum mechanics is by construction the linear theory. There is nothing non-linear.
What exactly?
But that is different, huh? Yeah, we'll come to that. Okay, don't bring that discussion right now, but we'll come to that. So now, what do I mean by observable? So observable is this. Anything some problem with my pen. Which depends on some problem with the pen, so I don't know what's happening. Okay, which depends on position and momentum. Anything that depends on position and momentum, in principle, you can measure in an experiment, and that is an observable. So one is position itself. Which is x in classical mechanics. It could be momentum. It could be momentum, which is p. If in one dimension it is px in x direction. Could be kinetic energy. What is kinetic energy? This is kinetic energy. Could be potential energy, which is usually v function of x. Okay. Some issue with the pen now. Check. The function of x. Okay. Fine. Now, these are observables. And what do you mean by linear and operator? So, first of all, it tells you that this is in classical mechanics. This is in classical mechanics, and this is classical mechanics. And when you go to quantum mechanics, you also have operator for each observable. So for x, it will be given by x.
Hello.
Yes. Any problem?
Yeah, sorry. No. I have a connection issue. Okay. All right.
Yeah. So I'm saying that for x, you have x hat. In quantum mechanics, we'll see what is px in quantum mechanics. But what do you mean by an operator? Operator means it's something which performs an operation. And in quantum mechanics, this operator has to be linear as well as Hermitian. Okay. So let us see what they mean by linear operator or operator. So, for example, I use this notation A with a hat. This is the operator, and take any function. Okay. Take any function. Okay. Take any function, and for example, if I take a function like f, and if I operate on this function f, some problem with writing, just doing perfect 5 minutes back. I think some issue with the PowerPoint. Well, I hope I can write. Okay, when you operate this on a function f, it gives you another function g. This is an operation. Operation, for example, I can have an operation like taking a derivative of a function, say f, which is a function of x. And when I take a derivative of this function, it will give you something, and I can call it another function, g of x. So taking derivative is an operation. Taking a square root is an operation. Taking a square is an operation. So I can have many such operations. But in quantum mechanics, the operators are such that they are linear. Now, what do you mean by linear operator? A linear operator is such that if I have this operator A operating on sum of two functions, say f, if you want to call it f1 and f2, then it is equal to A operating on f1 separately plus A operating on f2. This is how it is. Is this clear? But it may appear very obvious to you. Do you think this is obvious? How many of you think this is obvious that it has to be the case? How many of you? How many of you think this is obvious? Any second thought that this is not obvious? So let us choose to let us make a table.
Hello.
Sarah is saying something we can't hear anything.
So let me check.
It's working now. It's working now, Rashida.
It's working?
Yeah.
Yeah, working. Okay. Okay. Good. Some issue with what I'm going to do now. I'm going to wrap up for today. I think there is interruption, and I think we can wrap it up. Just few more minutes. What I mean is that, okay, this is not obvious. Can you hear me, all of you? This is not obvious. So depending on the operator, you can have a situation like this. This is true for operator like taking derivative. But if I define an operator just by taking square, this is not the case. So taking a square or taking a square root is not linear operation, but taking a derivative is a linear operation. So we'll stop here today. Okay, so linear, and from the next class we'll talk about what do you mean by Hermitian, and we'll eventually by next class hopefully we'll finish postulates of quantum mechanics. And please listen to the lectures of Professor Sebastian, lecture number 4 and 5, not 3rd. Lecture 4 and 5 on YouTube. Okay, the 5 is on path integral, which we are not going to discuss much, but lecture 4 and 5 are on the postulate of quantum mechanics. So please listen to these lectures. I'll send a link by the end of today. Okay, is this clear? So far you have any question, please ask me questions. Maybe a few more minutes, but we'll wrap up little early today because it's quite heavy. Significance of normalization of wave function is that your probability has to be normalized, because your probability is finite and your total probability is 1. That is how you normalize your function. Yes, any other question?
Sir, what is the problem if the quantum mechanical operator will be non-linear?
There is no problem. Again, I told you, no, the problem is this is how these postulates are built. So you don't question these postulates. Actually, it is possible that you build an operator which is non-linear and
yes, sir. Okay, sir.
Yeah, and do the quantum mechanics. But maybe Rahul, you can tell something because you are doing couple cluster.
Yeah, I
Rahul,
mean,
you want to comment? Yeah.
Yeah. So basically, the nonlinear operation. I mean, you see, the nonlinear terms are usually done. So first of all, you need to understand that what is the operation is not a measurement.
Okay,
the operation is not measurement. By quantum mechanical measurement, it's something different that probably Professor Chakraborty will come to next class. But operator is simply a mathematical relationship. Okay. By mathematical relationship, you mean if you have a nonlinear operator, what usually happens is that your operator depends on the solution.
Yes. So actually, your operator depends on wave function.
Your operator, the construction of the operator depends on your solution.
Yes.
So that's the typical case of. So nonlinear case doesn't mean that it's if A is a linear operator and A square is a nonlinear operator. No. By nonlinear, what is meant is that your operator does not depend on your solution. Okay.
But in quantum mechanics, it is always linear operator.
So that's what it means by linear operator, that your operator does not depend on your solution. We always build up cases where your operator depends on the solution itself.
Yes. In couple cluster and also
I will teach you some part in that one when there is this multi-electron system. You often have to go beyond your linear operation because of the fact that your operator will be dealt with some of the solutions that you get by solving that particular operator. So it's an iterative procedure, in other words.
Yeah. So, and square integrable actually means that you integrate it and you find it finite. That is square integrable, and that is important. Somebody asked that question.
Yes,
probability has to be one.
Square integrable thing, that is like, what is the difference between being normalizable and being square integrable?
Same. Just different words. If it is square integrable, then you can normalize
They
it.
mean the
Yes,
same.
yes.
Okay, sir.
So I can give you a not an interpretation, but sort of a similarity to what does this wave function mean actually. So if you go back to the double slit experiment, okay. So if you go back to the double slit experiment, you see that in the case of wave, how did you write down your total probability? You write down your probability. The measure of your probability was your intensity, and it was just given by the wavefront, the height of the wavefront squared, right? So say I have two wavefronts, one from hole 1 and another from hole 2. If you have the corresponding heights h1 and h2, so you wrote down your total probability as h modulus of h1 squared plus modulus of h2 squared plus twice h1 h2 cos theta. Theta is the phase difference. You remember that the electron wave, the matter waves, they do also follow this wave pattern, right? Because you see the interference pattern in your electron wave. So just like your pure, say, water wave, you can write down your probability by some complex number which is equivalent to your wavefront amplitude, phi1 squared plus phi2 squared. By phi1 and phi2, I mean the wavefronts passing through slit number 1 and slit number 2, and 2 phi1 phi2 del theta, right? So your phi1 and phi2, which we have interpreted, or psi, whatever you call it, which you have interpreted as your wave function, this is nothing but your probability amplitude. It's amplitude of your matter wave. Okay, so it's the amplitude of your matter wave, and the interpretation is that this probability amplitude is additive. That means you are writing the total probability in terms of your interference as phi1 plus phi2 entire thing modulus squared, which is basically given by phi1 squared plus phi2 squared to phi1 phi2 cos theta. Okay, so it's basically the probability amplitude is additive. And see, if the probability amplitude is additive, so the total probability is nothing but the square of that one. Or the probability density is basically the square of that quantity. So that is given by phi squared. So see that this phi squared, this quantity, probability density, or if you multiply it with the volume element, the total probability, this is in sync with your definition of your Heisenberg's uncertainty principle, because again, the uncertainty principle automatically guides you that you cannot get the position, I mean, with infinite precision, right? So that is always associated with the probability, not a certainty. Okay, so the interpretation of your quantum mechanics that your psi squared is a probability is in sync with your Heisenberg's uncertainty principle. It gives the probability, not a certainty. Okay, is this clear?
Yeah, we can actually discuss. And okay, one thing I'm going to now stop recording. It's taking some time.
All right, Rashid, I'm logging off.
Yeah, I'm also leaving.
Yeah. Somebody said whether to write it down in any slide.